Chart 1. This briefing is provided by Gregory Heinen to UAVForge. Perusing multi-rotors. Keep U angle of attack positive. A vehicle solution class for the Perch Stare Mission. Chart 2. Background and skills. Mr. Heinen has been involved with intelligence, surveillance and reconnaissance missions for 25 years, and has a variety of hands-on experience with a range of vehicles and missions. Most recently, he is supporting the warfighter with the Battlefield Airborne Communications Node mission in theater. He also has a background with heavy fuel engines and power systems for a range of small vehicles. Chart 3. Objectives of this idea video submission include high thrust to power ratio rotors, incorporating a lift mechanism into a multi-rotor, designs to achieve positive angle of attack cruise, something that most multi-rotors do not do. Also, we hope to minimize balance and center of gravity issues with multi-rotors, and alignment issues. Acoustic baffles are integrated into the design, as is the support frame hull. We promote use of maneuverable drop-down adjunct payloads. Chart 4. Issues with multi-rotors include the negative angle of attack, poor lift to drag, alignment and performance limits with low bandwidth rotor control, limited to 1 Hz. Acoustics tend to be unabated. Chart 5. The pack Pigeon packs and 2 MOLLE rucksacks. The Skeet is our model for aerodynamics, similar to the Frisbee. Flight speeds are in the 45 to 85 mph regime. A nice compact turboshaft engine is the Jakadovsky engine from Germany, or the rotating cylinder valve engine, with good performance. Again, we believe in the drop-down payloads and the vehicle acting as relay or the beacon airborne assets. Chart 6. The winged version of Pack Pigeon is similar to the Hawk wing, with a front and rear wing. The disc could employ lifting shapes, such as one finds in a Skeet. That shape is not shown here. This is a quad-rotor vehicle using flow control for attitude and thrust augmentation using 2 electric ducted fans for higher speed cruise. Chart 7. This chart shows the components from a bottom view. Depth of the representative 38-inch width disc is 4 inches. The power module, payload and fuel sections are shown. Chart 8. This chart shows a pure disc Pack Pigeon which in the prototyping phase, before composite work has completed. The sizes are shown. Again, we use flow control with servos and vanes. The front lip at the top is a Skeet lip with stepped ridges. This is a form of high lift mechanism for the slower flight regimes around 60 mph. Chart 9. This chart shows a drop-down payload with tracks on top and bottom, so whatever side lands down yields traction. It can be maneuvered forward, reverse and turns. The vehicle senses an upside, and the camera boom raises to 1 meter. Chart 10. The key to meeting mission timelines is the efficiency in cruise and hover. We employ high thrust to power rotors. Cruise efficiency is afforded by the lift of a wing version or the disc version with arrow shape. Chart 11. These photos show development of circular, rectangular and multifaceted quad-rotors. Various forms of the vehicle are in test and in development within X-Plane. Have been developed since 2009, first flown in X-Plane. Several have flown in cruise mode on 1 to 2 kilowatt quad-rotors. This shape disassembles into a MOLLE pack. This chart shows the history of some of the component development, gimbal test, flow control, power systems, multi-bladed geared rotors, and drift control with optical flow sensors. Key components shown include arrow shape, high thrust to power thrusters, flow control, IMU flight control using Ardu pilots integrated with Sente optical flow, and power systems. Chart 14. We have performed several size, weight and power assessments for various vehicles. This vehicle meets the mission requirements and weighs in at 36 pounds, fully loaded with fuel and payloads. Charts 15 to 17. For attitude control, we show the various pitch orientations using flow control. We do not use differential rotor control except for yaw, shown later. The next few charts shown roll and yaw. Chart 18. For more information, email me or message me on UAVForge. You can also check out some Google documents. Chart 19. We envision teaming to be a key to success. Nearby is iRobot and Kinetic. I have also developed relations with University of Massachusetts Lowell and Sante. We are open to ideas.